see this periodic table, we're going to mark some regions. The regions of this periodic table, and if you can zoom in on this as much as you can just on the periodic table itself, mark the following regions. The first two columns right here, sort of circle around those or highlight those and call that the S block. S block. They are called the S block. The first two rows, the alkali metals and the alkaline earth metals right here, are the S block. The center section, right here, the sunken down section where we learned the transition metals were, in that center section there, are called the D block. So you can sort of do a little bracket kind of thing and say that's called the D block. This section over here, with the exception of the thing on top, the helium is also part of the S block then, so you can sort of draw an arrow back to that. This section over here, square over here, is called the P block. Anybody want to guess what the bottom two rows are called? Which block are we missing? F block. Right, they're the F block. Now that we know the blocks, we're going to start filling in a pattern here and understanding. All right, so let's start where hydrogen is. Everybody start where hydrogen is. And in that block, I want you to write 1, a small s beside it, and then an exponent 1. Where helium is in that block, I want you to do the same thing, but change the small exponent to a 2. 1, S2. Now, here's the pattern. Underneath hydrogen, as you're going down, you're going to change the number in front. You're going to change the coefficients. So it's going to be 2s1, 3s1, 4s1, 5s1 as you move down. Underneath where helium would be, which is right beside that, you're going to do 2s2, 3s2, 4s2, so on and so forth down. All right?
What was in the second row?
2s2, 3s2, 4s2. So it's S2s, but it's called the S2 block, but it's just changed number in front. Now the P subshells then, we're going to go to the top left block of the P block. Okay, top left block of the P block, where boron would be, right here. And in that block, we're going to start with 2, because it's in the second row, 2p1. Yep. As you go to the right, you're going to add to the exponent. So it's going to be 2p2, 2p3, 2p4, 2p5, 2p6. So you go to the right across that row, add to the exponent. And then as you go down, change the coefficient. So underneath that, it's going to be 3p1, 3p2, and then 3p2, 3p3, so forth and so on as you move down. 3p2, 4p2, 5p2, 3p3, 4p3, 5p3. So change that. Pause there, Nick. The D block is next, starting in the D block right here in the top left corner of the D block, which is that sunken down section. It should be, I think, scandium there. I think that's the first one. Is that right? All right. So starting there, we start with a 3D1. 3D1, because third row down. Third energy level, actually it's not third row down, it's fourth row down, but remember they're one behind. The D subshell is one behind where the S's are. So 3D1 is there. And then as we go to the right, what do we change?
Exponent.
Exponent. As we go down then we change the
Coefficient.
So 3D1, 4D1, 5D1, 6D1. As we go to the right, 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, so forth and so on. And then the F block does the same thing. That same pattern exists, but it starts with 4F1. Because that's what the first F subshell comes in as the fourth energy level. So 4F1 all the way up to 4F14, 5F1 all the way up to 5F14. Alright, now we're ready to proceed with what we use this for. What we're going to use this for is how you determine electron configuration. What we're going to do is look at electron configuration. What electron configuration is basically doing this, figuring out where all your electrons are, without having to draw all the arrows, draw all the dark charts. By simply looking at a periodic table and following across, you should be able to figure out the configuration. And here's how it works. if you have an element, such as aluminum, and you're asked to determine the electron configuration, or if you need the electron configuration, what you're going to do is you're going to start in the top left, and you're going to go left to right across your periodic table until you reach the element. As you fill a subshell, you will write it down. So for example, aluminum's going to be right here. All right, everybody agree with that? Aluminum's right there. That block right there. So we go across the first row. We go through the 1s subshell, and we're done with it. Have we reached aluminum? No. So for the configuration right now, 1s2. That means in the 1s subshell, I have 2 electrons. We come back to the left. I continue across. I've completed the 2s subshell. Have I reached aluminum? No. So I write down 2s2. I continue across the 2p subshell. Have I reached aluminum by the end of the 2p subshell? No. 2p6. I come back to the left. I go across. 3s subshell. Have I reached aluminum? Nope. 3s2. Finally, I reach aluminum. Where do I reach aluminum? 3p1. So I write down 3p1. Now from that, we have our electron configuration. Now, what is the electron configuration? Why is it so important? Well, it's important to us because as we journey on through the next couple chapters, we're going to focus back on that word valence electrons again. Electron configurations help us understand how many valence electrons we have. So in this case, what is our highest energy level that we have for aluminum?
3p.
Well, what's the highest N value for any of these? 3, right? I have a 3 here. I have a 3 here. So this are my valence electrons. These are called my inner core or my core electrons. Now why is that important to me? Because inner core electrons play no role in bonding. They don't play any role in bonding. They're there. That's it. All right? The valence electrons are the only ones that will be reactive in bonding. Now aluminum has how many valence electrons? 3, because it has 2 in the S subshell, 1 in the P subshell, for a total of 3 valence electrons. All right, so since it has 3 valence electrons, it has 2 options. It could go pick up 5 to fill up the P subshell, or it could give away those 3, making this the valence shell, and it's now full. Which is easier to do? Pick up 5 or give away 3? Give away 3. So this 3s2, 3p1 is the configuration. It tells me what's going to happen with aluminum. By looking at a configuration, we understand what it wants to do. It wants to lose 3 electrons to be happy. Now, because these are the only ones that are important, we also have what's called an abbreviated configuration. Because as you go further and further down that chart, you can see it can get pretty time-consuming writing out that whole configuration. An abbreviated configuration simply starts at the previous noble gas. Because these guys are the same as the previous noble gas. All the inner core electrons are the same as that. So doing an abbreviated configuration, or what we call a core configuration, or an inner core configuration, would be simply this. Aluminum, what's the previous noble gas from aluminum? Neon. So we start with neon, and we say neon core. So when you see brackets like that, neon inside of it, that means everything in the inner core electrons are the same as neon. And then after neon, what do we have? Well, after neon we have 3s2, 3p1. All right? That's the configuration for it. Now, if you're given another element, let's say I'm given titanium. Let's recap again how you do this. To find the configuration, you first find the element on your periodic table. Where is titanium? It's in the D subshell, right?
3d2.
How far over is it? Is it in the 3D subshell? 3D2. All right, so it's right there. Now, unless I say otherwise, or unless the problem or quiz or a test or homework says otherwise, you are welcome to use the abbreviated configuration. All right? You are welcome to use it unless it says give the full configuration, or the choices on the test or the quiz are a full configuration. All right, so let's do the full configuration real fast. it would be 1s2, 2s2, I've gone through here, I go through the 2p subshell, 2p6, 3s2, 3p6, I come back to the left, I go through the 4s subshell, 4s2, and then finally I get to it where 3d2.
No battery.
Okay. So, in this case, what did we learn about the transition metals? They fluctuate in their charge. Why? Because they have some deviations. Now, here's what I want you to look at. Real quick, look at your periodic table that I gave you, the one that you downloaded and printed. If it's mine, if it's not mine, then you won't be able to look there. Right above the element symbol of the one I had on the website, you'll see the little configurations there. It says like a core, it'll say like a neon core, and then it'll have a little configuration. Everybody see those in the ones I printed out or I gave you? Those are not always correct, so don't abide by them. For some reason, they're not always correct. The reason why they're not always correct is because there are some deviations in some fillings in the transition metals. We don't cover deviation. If you cover AP, Mr. Walker or AP will talk about deviations in that and why they deviate. For this class, we don't talk about it. So when I ask you to do them, do like I'm showing you here. Now, what would the abbreviated configuration be then for this? What's the previous noble gas? Argon. So we put brackets, argon. And then after argon would be 4s2, 3d2. What's the valence shell? What's the highest energy level? 4. How many electrons are there?
2.
2. So it has 2 valence electrons, but it has 2 more here. Now the way you're going to learn later to tell valence electrons is look at the Roman numeral above the periodic table. Above that column, see how there's a Roman numeral there? That tells you the valence electrons. So that tells you what it tends to do. So the number of valence electrons can be determined by looking at electron configuration, which is that. So the transition metals especially go by that number. All the others you should be fine figuring out. But by that one, these get confusing because people say, wait a second, is this or this the valence? Theoretically speaking, it has 2, but some of them do some deviation. So what is above that column? 4 is above that column? All right, so we're going to say it has 4. All right, so follow that for valence electrons.